Okay, thank you. So I don't have much time. I made this talk a little bit also technical, and a little bit non-technical. So we'll see how it goes. I'll be happy to take feedback into account and change the way I'm going to present. But basically, this is sort of like a foray into what the future of spectrum sharing might look like, and what role, as Linda pointed out, for example, AI is being considered one of the key components of future wireless systems, what role it may play, and what things we need to be careful about. So I'm going to just jump right into it. So just a brief review. I'm not going back to the development of the first neuron by McCullough and Pitts, but starting with, for example, Turing in 1950, where he proposed the Turing test. And the AI or machine learning world has been going up and down in the last 70 years or so. We had the first, if you see after. For example, perceptron was proposed. There was a big hype. Then things fell down. We had a first AI winter. Then we had the expert systems, and some neural network, multi-layer neural networks came back in a big hype. Then again, it couldn't achieve the goals. Second AI winter came in. Then we went more towards the statistical learning world. And that kind of plateaued till we had deep learning, and now we are all in the world of what we'll call AI Spring, where the promise is that, and it's quite a true promise, that AI can revolutionize pretty much every field of technology or different walks of life, including from, of course, the tech industry to how we teach people, medical diagnosis, and so forth. So it's then no surprise that we are seeing more and more that people believe it will fundamentally also, as Linda already mentioned, is going to reshape the wireless landscape. And this is just some recent articles just I collected, including, there's funding happening in the industry, NSF, Intel, DARPA, they're all pouring money into AI with the belief that AI will fundamentally shape how we run our wireless networks, how we will engage in spectrum sharing, and all those details. So this is all good, and this should all be cause for celebration because of a number of things that AI would be able to do for us in the spectrum world. But we also have to be a little bit careful, and in terms of what are the dangers if we rely on AI without actually thinking about what could go wrong. In the world of wireless, we will of course see what could go wrong once commercial things with AI embedded in them start pouring in. But we have already seen what could go wrong outside the wireless industry. We already know how, for example, social media algorithms, which were one of the first to move to AI and machine learning, how they were duped into, for example, peddling fake news, and how extremely confident researchers who felt that, for example, their self-driving things going into Uber or Tesla that could not go wrong, actually ended up, unfortunately, costing us lives, right? Where the reality was that these things were more brittle than we thought they were. And especially in the world of, for example, this Uber incident and Tesla, and now actually, if you talk, a lot of self-driving companies are saying, well, it's actually not, we probably won't see the complete autonomy of self-driving cars. And this was even without doing any kind of nefarious activities or malicious activities. So the lesson from this for the wireless industry, and especially when we are talking about spectrum sharing and spectrum sensing, is that things are going to go wrong, and we can either wait for things to go wrong when the time comes and fix them, or we can try to actually design our algorithms, design our systems that proactively look for things that we know would go wrong and try to fix them. So this is a little bit of a talk in that direction, where the focus more is on spectrum sharing, what the spectrum sharing world will look like in the future, where we may have multiple sensors, or perhaps different drones, or the sensors might be sitting in cars, or there may be collaboration across different companies. Who knows what the landscape would be? But one thing is clear, that it will be a very decentralized, if we want to truly do spectrum sharing with the maximum spectral efficiency, it will be a very decentralized, distributed content, where we'll have data distributed across different sites. And we are now trying to run machine learning algorithms on those data sets to make decisions, sometimes even sub-milliseconds decisions on, okay, shut that device on, shut this device off, and so forth. And one of the things is that when you are in that decentralized, semi-autonomous groups acting together, how do we make sure that not only we account for problems that may arise due to bad engineering or algorithms that are not robust, but also how do we basically make sure that if there are bad agents in there who are trying to, let's say, hog your spectrum, or do cause some other kinds of crashes, that our systems don't break down. In particular, they don't break down even if we don't fully understand the black box nature of whatever AI or machine learning is doing. So this talk is sort of like, this is sort of like the major, broader vision that I wanted to present. And after that, it's basically going to delve into a little bit of technical details in terms of some of the work that our group has been doing to actually circumvent these challenges. So these challenges can be addressed in two different scenarios. One is what we call distributed setup, where you have a central server and all the decision making is handled through the central server. This could be one model for some spectrum sharing or wireless networks, or we could have the decentralized setup where a lot of different entities come together to perhaps help the group as a group make decisions. And we are going to focus on the decentralized setup because many of the solutions that we present for decentralized can be mapped to distributed in an easy manner, but the vice versa is not correct. So, so the way to study these kinds of problems is basically we have to go back to the foundations of how we look at machine learning problems. And one of the ways to think of a machine learning problem is just solving a stochastic optimization problem. You are basically, you are given some rule f, and which is it could be it's a loss function, for example. And you are trying to, in machine learning, you are trying to learn some model W using minimization with respect to some data Z. In classical signal processing or communication, for example, we assume that we know this distribution of Z very well and we can solve this problem. What machine learning says is that I don't need to know the distribution. In fact, the distribution, it may not be easy to learn that distribution. Instead, what we can do is what's called empirical risk minimization. We get a bunch of training data. So I have n training samples. And by the law of large numbers, instead of doing this expectation, I'll just take average of that. If my number of samples is large, I hope that this average converges to the true solution. And indeed, that's one of the results, that as the solution that you obtain by solving this problem converges to the true solution at a rate of 1 over square root of n, where n is the number of samples. So this is pretty old result. This holds in centralized settings. And in the decentralized setup, when we go, is the setup can be formulated since we have to do some abstraction, we say that we have m different nodes and each one of them is given some data set. And now the nodes are collaboratively trying to solve the same problem. At the same time, every node is making sure that they come to the same solution because they are trying to all work towards one goal. So all the nodes are learning some model, machine learning model, which is called WI or W1, W2, which should all equal the true solution. And there are many algorithms that actually exist to solve this. In the last 5 to 10 years, they have come about under different branches in terms of distributed optimization, decentralized observation. There is a lot of interest these days in what's called federated learning. That's also related to this. So all of these things work great. You can get also very good guarantees that show that, in fact, when you have M entities, agents, nodes, data centers, whatnot, each with N samples, when they collaborate together, their learning can be better than anyone doing individually. So that's sort of like the motivation for also collaboration. And of course, sometimes you all don't get to see some data distribution if you don't have some other one person collaborating with you. So these are all very good set of results, except that none of these results actually look at how what would happen if there were some kind of failures within the system. The failures, as is discussed, they could be either because something failed because of engineering reasons, but also it could be because there is a malicious person or agent or entity trying to actually actively sabotage your algorithm. So it turns out that actually this is because of the literature on distributed systems, like distributed systems have been used in computer science for a long time. People have studied this under different contexts. And in particular, one setting people have looked at is what's called the Byzantine generals problem, which is that you cannot make an assumption about what the malicious user will do, what the actions would be. And so you have to basically account for the worst case scenario. This is very different than what happens in, for example, communication systems, where most of our things are built for average case scenario, because we know that, occasional deep outages or whatnot will be very rare. So let's build the thing for average setting. In this case, we really have to look out for sort of like the 1% doctrine, which is that if there's a chance someone could break it, we need to plug that, because out of a huge collection, millions of users, even if one user acts maliciously, it can bring down the whole system. So the goal becomes that you can pose that problem by saying that you have a collection of M nodes where some of them are now not trustworthy, but you don't know whether they are trustworthy or not, because someone, let's say, had a cyber attack on that device and it was taken over by someone else. So what you need is you could take two approaches to it. One is you could say, I'll always look for if someone is going rogue. But as we know, or in the world of security, it's called zero-day attacks, which is that when a vulnerability becomes open, the hackers or the cyber attacks happen right then and there before you can actually plug the holes. So how do you actually deal with those? Well, you have to have a system which says, I'm going to collaborate with everyone, but I'm going to trust but verify. So you have to basically come up with a solution where you say, I don't know which node might be compromised, but I am going to work with everyone. I'm not going to say, oh, you are bad, I'm going to kick you out, because that may take you a while to figure that out. Eventually, of course, you want to do that. But while we are actually in an active running setting, how do we make sure that the solutions we learn at all the good nodes are the right solutions? And also we achieve the advantage of collaboration that we discussed earlier, which is that the learning rate, as it is called in machine learning, is better than any one node's individual learning rate. So there are a lot of works that have looked at similar problems under some restricted models, but none from the perspective of this statistical learning setting. And the question is, can this problem be solved? It turns out that yes, under some technicalities, with some under some appropriate conditions, you can actually, in fact, show it very in a mathematically rigorous manner that it is possible to actually solve a problem in a decentralized solution, a machine learning problem where all the nodes that are good get the right solution and the bad nodes will not affect the solution by a large amount. And so what that gives you is this window where you can actually keep on operating while, let's say, a flag goes out or somewhere, and then you can investigate further and say, okay, I need to take this component out of the system because it has been compromised, right? So it doesn't it doesn't break your system down while you're investigating. And this is some sort of technical details that I won't go into. I'll just say that the algorithm that we have is based upon actually a simple idea. So robust statistics for people who might be aware of has been actually used to solve the challenge of outliers or rogue data sets for your problem for a while. And the idea that we use is to fix this issue is a very simple tweak of changing gradient descent, or in this case, we use distributed gradient descent, combining the idea from there to the idea from robust statistics. So without going into too much detail, I can just give you a simple setup that, for example, in Olympics, for many competitions, for example, when you have 5 referees and they each give a contestant a score, there is always that fear that, well, someone might have been bribed or someone. So what they do is they take out the score of the highest, the referee score, and the lowest referee score. Basically, they are trying to remove the outliers. This thing, and then they take the average of the rest of the referees and they declare that to be the score, right? This idea is basically is a similar idea, which is in robust statistics called trimmed mean. And the idea is that if you have a bunch of people collaborating, you're trying to come to a decision. Of course, mean in this figure, if you look at it, this is the mean. But if you just compute the mean and one person actually decides to jack up their values very high or very low, they can, the mean will deviate a lot. But if you use this idea of trimmed mean, while the person who has gone rogue can affect your score up to a certain extent, beyond that point, they cannot affect it too much. So you are within your margin of your true mean, and that's sort of like the idea that's used in many sports competitions to keep the referees honest, because you know that if you are an outlier, your score is actually not going to count. So it's a similar idea that we use where, you know, if you are collaborating with other users, then different users send you information, and what you can do is you can actually look at and get rid of the extremes and take the average, or use the information only of the people in the middle. And this thing leads to, I mean, the challenge becomes, of course, how do you analyze that? So that is what we do. I'm not going to go into the details of the technicalities. We have a very simple algorithm that actually can be incorporated into any, for example, machine learning thing, like, and we have theoretical guarantees that show that indeed the solution that you get, it is better than working by yourself, because you're collaborating with others. Your machine learning model is going to be better. You are guaranteed to not be affected too much by these rogue or malicious users. Everyone is guaranteed, the good users are guaranteed to arrive at the same solution, and so forth. So here's a basic sort of experiment that I'm showing, which is that if I have a binary classification problem and I use a classical algorithm where I have 50 people or 50 nodes or agents or whatnot, they are collaborating with each other, and I some of them go rogue and they take part in malicious activities. Traditional algorithms just break down to 50% accuracy, which means these malicious agents can bring you down to just coin flips. Whereas the algorithms that we have proposed can actually get you pretty close to the true accuracy. And if you were to just do things by yourself, of course, you are affecting. So these solid lines show this is what you would do if you were just acting by yourself or trying to do classification on your own data rather than collaborating with others. So this is sort of like the gap shows the value of collaboration. But when you collaborate, if you don't have a specialized algorithm, it can really break down your algorithm and bring you back to random coin flips, whereas this algorithm can save you. So since I am pretty close to my time, I'm happy to talk about technical details for those who are interested. Our papers are on the Inspire Lab website, and the code, if people are interested in running, is on GitHub. So the basic message that one should take away from this is the following: that AI, machine learning, is a very powerful tool, and it is likely to impact the landscape of how we operate our wireless networks and our spectrum sharing and spectrum sensing. But the issue of how it could be manipulated or how it could affect decentralized systems is very real. We have already seen that in the tech industry. We have already seen the effects of that in a number of industries, especially the unfortunate deaths in the self-driving car business. And we can either, within the wireless world, we can either implement them and then wait for things to happen, or we can actually think them from the ground up and say, we better make algorithms that are resilient to any of these backdoors so that we don't let anyone affect our operations later. So with that, I'll conclude, and thank you for listening. Happy to chat more about it through questions.